Yeah.
For APC, what is the change in speeds? You just find like the area that the curve tracked it.
1/7. All right. So, infamously, there's a man named Isaac Newton who went home on a vacation because there's a plague running through his city. Not the kind of plague you guys are dealing with, the kind that kills 50% of the population of the city. He went home to an apple orchard, which is where you hear about apples in Newton's lives. And he was given one job to do. That's to take those graphs you've been dealing with and turn them into different kinds of graphs. Distance time graph and a velocity time graph. So you had to sketch a bunch of tangents. All right, so he's doing a lot of this work. You know, here's my graph. He's drawing a lot of tangents. And then he was redrawing these velocity curves, the velocity time graph, and ending up drawing the new curve. Agreed? So that's what he was doing. He was told, he was given thousands of these to do, because they weren't sure when he was going to come back. He started working on Tuesday, we believe. By Friday, he thought he discovered an easier way to do all the work. By Friday, he started to think in a totally different way. He discovered that if you had a distance one that looks like, say, this, oh, it should be T, my bad. His distance formula started out like that. Then his velocity formula ended up looking like this. And his acceleration formula ended up looking like this. Likewise, if his distance formula started like this, oops, I shouldn't do that. Pick something suitably weird. Then his velocity formula ended up looking like this. And his acceleration formula ended up looking like this. Which makes sense, because that's d equals 1/2 at squared plus v naught t. b equals v naught plus at, and your acceleration is a constant 9.8. Shouldn't be shocking to you that that's true. He didn't know that at the time, by the way. He was still working at it in darkness on that. I'll give you another formula that he could have run into. It became a formula that looked like this. Let me give you a fairly famous one, or some I make it up. Then his velocity formula would look like this. And his acceleration formula would look like this. So Sir Isaac Newton spent time looking at this. And the good news is Roebuck and Rock are not allowed to talk anyways. By Friday, he started to see a pattern. What's the pattern? Nick, tell me something that you see.
Well, when it goes velocity to acceleration, it's it's not enough bottom.
Okay.
The 12 just kind of doubles up and 32.
Okay, so this one doubled up and this one stayed there. Okay, using your theorem. What about this one here? Does it double up? What does it do?
It triples.
Triples. So it tripled here and it doubled here. Yes, sir.
It's well, it's because in the first one you have 1/3, and the second one you have 1/3 I was looking at the comments, but
I mean, we're asking you to make the same discovery that Newton made, and it's a big one. It's huge. It's epic. And he had a whole weekend once he got the data in front. Well, yeah.
what
What's happening to the powers?
they draw.
They drop. Each time they drop by 1. 4 becomes 3. 3 becomes 2. That's not 3. 2 becomes, this should be a 1. Right? And then t to the 0, which is 1, right? So that's actually there. What happens here? This is t to the 0. T to the 0 becomes gone. That's a little disturbing because you can have t to the negative 1. So that doesn't seem to make much sense. But at least you can see it's dropping, can't you? Same pattern each time. Except for the fact it doesn't go t to the negative 1. Something weird happens there. The numbers out in front, you were darn close. Let me see if I can draw you in one more time just to fit.
Well, it's the slope.
Well, there's slopes. We know there's slopes. We know that's how you get from here to here, right? Because the slope of this curve is 9.8, so that's why you get 9.8. Yes, sir?
Only triple, like, on the bottom one, distance, you triple 4 to 12.
Okay, so I tripled here,
Yeah, and then you double.
and I doubled here. What?
And then for the left. It's because of the powers.
Powers. 3 times 4 is 12. 2 times 12 is 24. Newton looked at this and said, doesn't work every time. And he went through piles of paper and discovered it works every time. It took him another 10 years to figure out exactly what I should say. It took him a weekend to prove to himself it worked. It took another 10 years to prove to everybody else. He literally got this book together. He stuffed all these papers in there, went back to London. Remember, there's a plague. People are dying, but half the population is about to die in the next couple months. Goes back into the city with this great big book. Now, at the time, it was cool to write things in Latin. So he decided to call this calculations. And so Latin for calculations is calculus. This is calculus. When looking to change something to the rate of something, you simply drop its power, you throw its power out in front, you multiply by its power, and you drop it by 1. That's it. That's all it takes. You were going to say something?
I remember watching some video long ago, but that's how you can find the derivative
Right.
in cases where you can't do that.
Right. You can always find the derivative. More on that later.
Well, I'm saying that's one of the ways.
This is the way that involves the things we've been dealing with, which is arithmetic, which is polynomials, right? So all you have to do, if you're going to change one to another, is you take the power on the variable. Let's make this a b, make this an a, right? You throw it out in front, you go b times a is what you end up out in front, times t to the b minus 1. That's called the power rule. By the way, if you want to go the other way, it's pretty simple. You just have to divide by the, you raise its power by 1, then divide by the power you get. Congratulations, you just learned calculus. I wouldn't recommend it because there's some details. The details are troubling.
And going back up in the other equations, the number that pops up, how does that?
Let's do it.
Well,
Let's do it. No, that's a right question. Let's do it. So let's say I had this for my velocity, didn't know what my displacement was. What am I going to do? Well, I need to raise the power by 1, divide by the power I get. Divide by 4, this thing by 4, what do you get? 1/3.
How do you get the 7? Yeah.
How do you?
Ah, that's huge. That's our next discussion point. Good catch. Not yet ready to talk about that precisely, but we are going to talk about it before this period's over. There's no doubt about that. That is something we need to talk about. What that is and why it just disappears and why it can come back. Okay. So let's I don't know where my papers are. Oh, here we are. Okay, so. Okay, so derivative, what's the definition? Definition is finding the rate at which something happens. So for displacement, it's velocity. For velocity, it's acceleration. You take the derivative of velocity, you get acceleration. How do you take the derivative? You multiply the power by the number out, the coefficient out in front, and then you drop its power by 1. What does this represent in a graph? It represents the slope of the curve, or the slope of the graph. Remember, we have a bunch of these hokey graphs that look like this. And this is a displacement time graph, let's say. At this time, say 1, it has a speed. But we couldn't calculate why, because it's curvy. So we drew tangent lines, didn't we? Actually, this can be calculated if you can tell me what that formula is. By taking its power out in front, reducing the power by 1. That's it. That's all you have to do. Now, your calculus teacher is going to give you the actual mathematical reason for that. I don't have to. You just have to know it's true, because Newton figured it out well before you could figure out why it's true. Make sense? Okay, what does it mean in terms of kinematics? That means I can turn displacement into velocity into acceleration, and it does not need to be a constant acceleration anymore. Any acceleration. I write acceleration as a formula, fine. I just use this. If they say constant acceleration, you can go back to d equals 1/2 at squared, d equals v naught plus at. And there are a lot of things that have constant acceleration. But if it doesn't have constant acceleration, you're in calculus land. Now I'm semi-ignoring the boys that are on the box. Talk to me. You guys all good? The Villa must. Okay, Phil's back with us. That's good news. Oh, okay. Are you guys okay? Yeah. Well, Brock and Rob up to know why this didn't develop. Look. Yeah, here. Okay, I'm going to make a video of this and I'm going to drop it into the Teams box, okay? From the start to the finish. Okay? Alright. Alright, next on our list of fun-filled festival of fun, what's an integral? Integral, the definition of integral is finding the area underneath the curve. And we know why that's significant, don't we? Allows us to go the other way, doesn't it? How do I do it? If I have something that says a t to the fourth, or sorry, to the b, I raise its power by 1. Raise its power by 1. Whoops. And divide by the power I get. Do the process backwards. Instead of multiplying, I'm dividing. Instead of reducing the power, I'm adding power. Uh-oh. Let's pause the video.